works with this. So can I share my screen? Do I have the permission?
Yes, I can give you an introduction and then, but I let you to be able to share the screen.
Okay.
Okay. Hello and welcome back to another Core Lab lecture series. Our today's speaker is Dr. Hadi Hajibeygi, Associate Professor at the Faculty of Civil Engineering and Geoscience at Delft University of Technology. Dr. Hajibeygi got his PhD in mechanical engineering from the ETH University. During his PhD, he developed a multi-scale modeling and simulation method allowing for error control and reduction for multi-phase compressible flow in fractured porous media. After his PhD, he moved to Stanford University as a postdoc fellow at the Department of Energy Resources Engineering. And at the moment, he's an associate professor at Delft University of Technology and guest professor at University of Stuttgart. Dr. Hajibeygi is also hosting a public webinar of frontier researchers in the field of geoscience and geoenergy. These webinars are every Thursday at 4 p.m. Central European time, and you can find them on YouTube as Geoscience and Geoenergy webinars. Today he is going to talk about ADMIRE, a multi-scale framework for subsurface energy storage in fractured geological formation. Thank you so much, Dr. Hajibeygi, for accepting our invitation.
Thank you very much, Mohammed, for the generous introduction. It's my true pleasure to share this hour with you all experts of porous media and share a few of our research, and mainly to open up discussion and hopefully a new future and longer period to have collaboration and connection for mutual interesting topics. So as it was introduced, I'll be speaking about the project which is called ADMIRE. It has a meaning: Adaptive Dynamic Multiscale Integrated Reservoir-Earth System Modeling, which is about subsurface energy storage, and we have started it last year. It's mainly funded by the NVO, Dutch National Science Foundation, and Schlumberger, Chevron, and Shell are supporting it. It goes to a larger program of Delft subsurface storage that I lead at TU Delft, which covers all the activities we do, from storage of greenhouse gases to storage of energy in form of green gas or hot fluids or pressurized fluid like compressed air energy storage, aquifer thermal, hydrogen storage, and green methane as well. So this is a specific project within that larger program, and I would just narrow it down. First, I would do a little bit a global introduction about this subject, and then I would follow the rest. Do you see the right screen? Or
actually, we see both of the.
So you see the notes as well. So I guess I should just simply change that and see if this now works. Do you see now the right?
Yeah.
Okay, correct. Fantastic. Okay. So the work actually is mainly focused about how do we handle fractures in the subsurface, and I'll put the context in a couple of seconds from now. A lot of colleagues have collaborated to get us to where we are today, and still having a lot of questions still left. Directly, our PhD candidate Musa Hosseini-Mir and some other researchers, Aryan, Jan Yodan, and Kees Faulk, my colleagues in Applied Mathematics Department, are directly involved in the report I am presenting here today. Also, other students and collaborators are also contributing to what I am going to present. To start, I'd like to just give you a little bit of perspective. Where do we stand in terms of energy consumption and energy need in Netherlands? And to some extent, and to large extent, it would also hold for Europe as well. In 1 year in the Netherlands, we consume about 800 terawatt hour energy. And that is the total energy consumption of the country. It is in the form of heat, electricity, and all forms. So it's collectively, we are consuming this much per year. And about 2019 and 18, there were not much of increases or decreases. We stay in this kind of scale to give you a little bit of perspective, where do we stand. If you would like to store this much energy, you would think of electrical based batteries. You would take the most advanced state-of-the-art batteries that are in the transportation business. For example, passenger cars, they are ranging around 100 kilowatt hour for a kind of 300 miles, 500, some sort of these sort of ranges of transportation for a family car. And that would need about 8 billion of those batteries to store this much energy. Obviously, you're not going to store for the entire year, but if you are thinking of a season with low wind energy or solar income, then you might think of running the country for a few months on stored green energy. Then you are going to think about alternatives, because also not only about the capacity, but also these batteries would require a lot of mining and a lot of materials, and they are not as green as the end product would look like. So alternatively, you could think of converting the renewable energy by electrochemical processes to different shapes or forms of energy. Hydrogen is one, green methane, for which you consume CO2 with the green hydrogen, is another. You have also thermal heat, which is very much motivated by the use of geothermal energy, because you need heat management there. And other forms like CAES, which is compressed air energy storage, and they are not really shown in this graph. Those green gas could be stored by larger scale quantities in the subsurface formation. And I'm gonna go to the details of it and see in what way we are working on this subject. And our government is also very curiously looking into this subject as well. Last year, there was a report published by the Ministry of Economic Affairs about potential or feasibility of looking at this type of option for larger scale storage. So we have both industrial and also policymaker and societal kind of support and curiosity to see, would it work? If yes, how? And that's a big pillar, or one of the major projects that we have in the Delft subsurface storage in general. Now let's review for the experts my own knowledge. So I see a lot of wise attendees here. So just to make sure to you all that I am also, like you, aware of it, is that the use of subsurface, if you think that, well, we have a space down in the subsurface formations, let's put energy there and we are gonna be fine. We all know that subsurface formations, geological formations, aren't new to us, but also aren't really known by all aspects to us as well. The scale that we would like to operate is at kilometer. The scale that the physics happen by large extent sometimes is actually at the pore scale on the other side of this graph. So what drives the microstructure of the transport processes, and many times reactive transport processes, and so at the end of the day, through some scale, crossing the scale in the physics and in the process, you end up with a larger scale subsurface formation that you would like to keep it under your control. That's the first challenge that I'd like to address today, is about multi-scale heterogeneity and most possibly fractured. The second is about uncertainty. We don't know how the subsurface formation really looks like. And especially the data that comes with it is not really perfect. And it comes with multi-resolution nature, which means that the data that we acquire from the subsurface comes from different sources, well logs, electromagnetics, and fiber optics sometimes, and then field surveys. And these data sets are sparse. And by the best practice, they are high resolution close to the well and pretty much low resolution further from the well. What we have then is quite a sparse, vague understanding of how the reservoir might possibly look like. But what we want is highly detailed information about the subsurface, especially if you go to lower and higher and higher resolutions as well. So matching, first of all, to know what problem are we solving is one, and then we can develop models and solving it and so on. These actually too remain in many, if not all, subsurface engineering applications as the main challenges to deal with. Especially for this subsurface, the storage of energy, the third comes very relevant. And that's the cyclicity of the story. You want to seasonally or weekly or daily based store energy in the subsurface formation. You're gonna load, unload. Frequency, volume, and the way you manage would all play roles in the way you would like to manage your subsurface. You have two main different types of the subsurface formations that you could utilize for this. One is shown in the left part, is the salt caverns. You can drill and find salt depositions that are available in the North Sea neighborhood. And Netherlands and Germany, UK also are sharing that. Zechstein salt, for example, formation. You can have these caverns, the blue caverns, and then you can simply load and unload your green gas in here. So you are cyclically injecting and producing your gas there. And this is the 4-minute video I recently have created to just show it to the public what the mechanism of this storage really looks like. What you are seeing here is that the salt layer is deforming time dependent. It has creep, it has viscoplasticity involved. So it's less of only linear deformation, but time dependency and especially cyclic loading matters for the integrity of the material and avoiding the failure. On the right, you see the porous rocks. You do cyclic storage, so you do injection production, and these are empty gas reservoirs, like depleted oil and gas reservoirs that you can use for storage. You could use aquifers, like saline aquifers that we looked at for CO2. Now you can use it for hydrogen and other energy storage carriers as well. The main objectives, especially to younger attendees here and those who would watch it later, is about, to experts it's already known, is that we need to store all the fluids, all the energy inside the reservoir. So you would avoid leakage especially. And you would like to maintain the purity. So it's quite different than CO2 storage in a way that you are injecting and storing, but you want it to be back with the same purity as well, and with the same amount as well. You want to minimize the trapping as well. So in that case, the process would involve cushion gas injection like nitrogen and others, and making sure this is happening there. In the salt cavern stage, you have sump and brine deposition in the bottom. You may also increase humidity of this. And depending on the microbiological activities, you may also create other gases that you would like to avoid as well. So maintaining the purity of the stored fluid is extremely important as well, because you would not like to lose your gold hydrogen, for example, in this case, and have a little bit of other chemicals in it. And obviously we know that fuel cells are also not most efficient when the hydrogen is not really pure as well. If you use it for fuel cell, if for combustion, then you wouldn't really worry too much. And then at the end is also safe as well, which is also as important as the others, which is you would like to avoid critical stress. Now here I would like to stress on that critical stress point, which is when you do injection or production, it's a monotone loading of either pressurizing the reservoir or depressurizing the reservoir. When you do cyclicity, life is different. When you do cyclicity, many materials could really fail or could really behave differently, depending on how you are cycling it, how it is going to be healing itself, what's the deposition of the minerals there, do we have clays, do we have no clays? So this is a kind of critical stress, is not a static number. It actually develops, and materials have hysteresis, not only for fluid dynamics, but also solid rock mechanics as well. Now, with this setup, we have as I said, this project Admire is about the physics, simulation, and optimization of the subsurface storage energy. And we have started this, and we would be delighted to get help and work together with especially you all in Norway, in Oslo, that this is kind of a relevant subject for us, and we think that it is relevant subject for many of our neighborhood countries, and also in the just global scientific community as well. The page is just launched. It's going to be filled more with what we do, and every thing that we do also will be released open sources. I'd like to actually give a little bit of more technical depth after this type of global opening of my talk, and address one aspect of this complex system analysis. And I would like to focus my talk on how are we doing at Delft for dealing with heterogeneity and fractures, especially in our modeling and predictive or quantitative analysis of it. I'd skip the applied geology section, where they are quite busy with characterization, data acquisition. They have even drones that fly, and Marcel is now in Brazil. Many of our colleagues go to Brazil and take all these drone pictures and characterize it. I'll skip that. I start my talk with having some picture like this. And I know many experts are sitting in this call, so I'll share what I think would be appropriate to address this problem, and I'd be seeking your comment and feedback through the talk as well. So I'd like to first set my objectives with this. The objective of, if I want to simulate or understand and model this process, is that I'd like to have a conservative system because of the coupling and mathematical aspect of the transport process that happens in my subsurface formation. That's one thing. So whatever modeling approach I'd like to develop would be conservative because of my stability and correctness. Second is, any modeling approach that would be applicable for geological formations should allow for fractures, should allow many of them, and would be convenient for many of them. Because we are not talking about one or two in material science or composites or mechanical engineering, it's geosciences. You're gonna deal with these pictures that I'm showing, for example. And it should be consistent, obviously, because you need your errors to be under your control. You need to know where the source of error is, and especially if you're adding error because of your numerical scheme, you want it to go to zero if grid size is zero. So your discrete word and continuum word get closer and closer together. At the same time, geology says that fractures and faults can be highly conductive, they can be barriers, and they can be anything in between. And if you see that, if I can, from the picture here, I can tell you which fractures are highly conductive, which are not. It's not absolutely a trivial task to an expert as well. Depositions, roughness, there are so many aspects related to it that, again, there are people who are actually expert of it as well in the community and know as well, but this is for a larger community. And field scale relevance of our approaches are also important. I'm going to go to that specific detail because of the nature of the processes that we are looking at, and there are some global quantities that cannot be simply localized. And obviously, what we need to do is the sensitivity analysis should be relevant. We can't really look at the perfect exact solution. There are multiple acceptable solutions in our business. We have the wide variety of, this is the range of our outcome. And at the end, we would like to have a black box integration of what we're doing. We don't want to refabricate everything. Black box also allows us to have it connected to porous scale physics more appropriately, connected to existing modeling and simulators more appropriately. So it would be a modular integration of what we do instead of scratch-based approach that would require a lot of hand-based efforts.
Hadi?
Yes.
Can I just make a quick question?
Of course.
Could you just mention how the fractures could act like a barrier?
That's a great question. There are based on the mineral, like faults, for example. Faults are also like fractures, which are lower dimensional or cracks or failure in the material. And because of the depositions they have in themselves, they stop the flow from happening. They are impermeable. And they are anisotropic as well. They can be impermeable in different directions as well. It's more about the geological and the depositions of the things that go inside them. And sometimes a stress field, based on the way that the stress is exposed to this system and the history of the field, some of them become really like shale depositions. Like what makes shale to be shale? It's mineralogy, right? The grains are really tiny, they are stick together, so they are not really permeable. Now imagine these grains are also inside a crack, for example. That would make it sealed. So it's crushed, basically, type of things there. So, and they happen actually, and that's really something that then you would go to do modeling. Now, one class of modeling of them explicitly is that you would like to avoid kicking all of them out. You want to at least keep most relevant ones inside your computational framework. Class 1 says, let's put complex grids, but have convenient physics. Let's get the most state-of-the-art grading strategy, confine fractures at the interfaces of your grid cells in the matrix side. So fractures would be always at the boundaries of your control volumes. This has been started with many scientists there, and many more. I just listed a couple of people here to say that there are quite a rich community to address the fractures and discontinuities this way. And alternatively, you could look at it differently, and that's exactly what we are actually looking today at. You could allow the fractures or objects that have high contrast in your system be objects that are imposed on a computational grid that is convenient for your matrix rock domain. And then you can have them all fly and change them. If you want to especially do sensitivity analysis, you would be able by your pen on your tablet change the location of a fracture and see how the orientation would impact the outcome. Now the story is not new to the geosciences. It started in 2000, early 2000, and so with Song Lee at Chevron, and he was also my mentor at Chevron the time I was working at Chevron long ago. And then I also did that work as well with Patrick in ETH, and then later on many actually colleagues have been working on this subject. Now the story comes also relevant with fluid mechanics. Look at the problem as well. The branch of methods of called immerse boundary methods, where you allow an object to actually be independently described explicitly in a computational domain that does not change its geometry due to the existence of this. In fluid mechanics, a lot of progresses and developments have happened on that line as well. Here, it would make it more like well modeling. You have well injections, and so you don't really grid around the well, you allow the well to exist. Now, I have a specific object on this side because it is more convenient in the mesh. However, nothing is perfect. Here,
Can I ask a question?
Absolutely, please.
Yeah, this is Alex Hansen from Trondheim.
Yeah.
I'm looking at these fractures you have here, and it surprises me that they actually pass through each other, like they don't see each other. Usually you get T junctions.
Oh, right. This picture, that Alex, great questions. The thing is that these are just graphics illustration for my talk purpose. They are not really coming from the geology. I have geological maps in a couple of slides to come, if that's specifically about how I am.
Yeah, right. Okay, good, wonderful.
But they can cross each other.
Yeah, they can, but the typical thing is that you get these T junctions.
Sure. That a very relevant point. But in general, you would like to allow them to progress, especially if you allow fracturing or some extension of their geometries. But right, you may get different topologies that are not really seen in here. But Alex, if later on I am also missing those structures, I would be pleased to get those to include. Absolutely. Thanks a lot for mentioning that part. There is also a nice paper about benchmarking all these approaches by Bernard Flemish and Inga Berre and other colleagues, Florian Doster, is also written down there as well.
Yeah, actually, we did a lot of work on this a few years ago with the people in Rennes, Philippe Davy and others, to characterize the topology of fracture networks.
Oh, that's great, Alex. I'd be pleased to speak with you about, and I'm sorry if I have missed that so far as well, but great that that's the purpose of this webinar, actually. Great, thanks a lot. So with that, I'd like to go through this EDFM approach, which is embedded discrete fracture modeling. And the philosophy here is this. You want to simplify the computational grid because you would like to allow geologists to be convenient with drawing any fracture possibilities they have. And now here comes the payment for it. You need to be careful with the modeling and discrete quantities. Your discrete approach should be more advanced, should allow for it. Otherwise, it's not just as convenient as the other alternative, which is unstructured DFM, which is UDFM. There, all fractures are always at the interfaces. Here, they can cross you. And especially, Marcel just asked, you have a fracture that is sealing, now it is crossing over your element. You need to make sure the flow stops. And that's not a trivial task at all. So I'd like to review for you the most recent work that we have done on projection embedded discrete fracture modeling, PEDFM, that was and is still one of the most cited papers of advances in water resource research. And it was published in 2017, 3 years ago. That's mainly one of the work of Matej Tene, who is now working with Schlumberger, did a PhD with us. And the concept here is allowing fractures to have high contrast with the embedded matrix, from conductive fractures to barriers and so. You need to know if the fractures are, when they are there, I can't use my mouse, unfortunately, you have on the bottom left part of the figure, a fracture segment that is crossing over your element I. To allow for any conductivity of that fracture, you need to know what's the projected interfaces between cell I and K and I and J. And that's exactly the corrections that you need to do in order to make a consistent embedded approach. If the fracture is barrier, you delete that part of communication between I and K and I and J. There is a little bit more mathematics involved in it. You would, in general, describe a transmissibility between I, cell I, and fracture F, which is the third line on the right box. Then you define a connectivity between F and K, F and J, so fracture would communicate with the two other cells, and the matrix cells I, K, J would also communicate if necessary. So with these kind of mathematically defined transmissibilities based on the embedded approach that you also extend on the EDFM one, you actually go now to the field, and this is the outcrop geological characterizations that we have received from our applied geology colleagues. Giovanni Bertotti does a lot of work. Also, he works in Brazil as well, and I believe that's also one of the Brazilian outcrops that he has characterized. The characterization digitals are also in the repository of TU Delft. I could also send the file to you if needed. And we just arbitrarily defined impermeable and permeable fractures in the second plot from the left. So I just said, let's just assume one of them is impermeable, another is highly conductive. So the colored plot that you see is absolutely ad hoc for this purpose of illustration. And heterogeneity behind these fractures also are ad hoc. We just said, let's imagine we have highly heterogeneous matrix too, because it's also reality. The embedded approach, if you're not careful with the communications of these transmissibilities that I said, is plotted on the top. And the projection EDFM, where you see the projected areas and do careful consideration, is plotted on the bottom. And you see the barriers are being honored, while the other one wouldn't really follow the barrier. Or the pressure profile in the left sees already a contrast because a long connected fracture is actually a barrier. But now this is again a toolbox that now if you have it, which you can have it, you could just draw your fractures on your embedded system and analyze any relevant field that you would like to. And it would not require complex grid generations that would then slow you down, or it may not be really even applicable for the complex systems that you're looking at. So that's the area that also we are seeking for, also collaboration and learning from those who know, like Alex mentioned as well, about the topology of the fractures and what systems, what networks could happen and how are they described. And then we benchmark. Yes, please.
So you had the Km and Kf on the top left. Is this matrix permeability and fracture permeability?
That's true. Yes, absolutely.
Okay.
The
so
left
along the fracture, can you also have changes in permeability? Or
yes, absolutely you can. Yes. So
okay. So in the model, you don't consider the fracture to be
absolutely.
like a fixed permeability.
No. You could actually define based on the element. One element of fracture will have one permeability, and you can read it from the file. It's more about implementation. I assume that they have done it this way, but this is how it should be. And this is since that you allow heterogeneity in the fracture domain as well, then you would simply would be generic in any value you get. But very good point, by the way. And then you would like to carefully benchmark it with the unstructured part. And so you would create some test cases to see if they look like. We did very early one, but I mentioned already there was a benchmarking test case that many folks contributed in that has a lot more rigorous analysis for it. And then you come to geothermal. So you don't have only mass transfer, but you have heat transfer. And heat transfer is a little bit complex because you have interaction of conduction and convection. You have both hyperbolicity and parabolicity. Conduction is more global, convection is more time-dependent local. And that would mean that you would simply start to inject cold water, produce hot water from the other side, and your fractures now could have heterogeneity, not just for the flow part, but also heat conductivity and convectivity as well. So then this would make you do that, and especially since you are now putting your fractures in embedded way, you could actually run any complex geometry model too, because they don't really need to be regraded, they don't have to be adjusted or so. You just define plates that are fractures or faults or barriers for you to direct the fluid dynamics part. And that is already released open source here, and you can, it's a MATLAB based one, so it's not open, you need free, you need 100 euros of license of MATLAB. But the rest is that we are extensively working on this topic, and we would be delighted if there will be any collaboration to do that. Especially I have many students who are working on this code. So if there is a subject, we can tune it, we can make it happen so that we can work on more advanced, let's say, physics. And I am going to speak about some challenges, but I would like to also, now that we are here at this slide, would also mention that especially with geothermal fields, we are in need of physics-based functions, upscale functions. I don't know what relative permeabilities I should put for my geothermal system really. I don't know if it's high enthalpy geothermal where steam and water exist. What is really a right relative permeability? If you even find it in the literature, I think there is no, but I rather not to say no, but we have found nothing to be physically real. And when there is, I can do mathematics too much. I can plot all these things. When the physics is not right, when geology is not right, I have a nice toolbox, but it needs to have the right numbers in it. I am working on my side to make the mathematics and the modeling part to be relevant, but at the same time, that part is also extremely crucial here. Especially in geothermal, as we go forward and becoming more interesting, more important, I ask even experts, what functions do you use? And there is no lab experiments that is rigorous as much as we did for water flooding or oil industry. And even for scale physics of it, how does the relative permeability and capillary pressure look like in terms of the geothermal systems? It would really be impactful study, and we would benefit, and we have even interest to invest on that subject as well, collectively. So with that, I would like to now go back to my question here. Do you think that would work for this plot? I mean, I can do these fractures. How many of them I can really do? Yeah, this is 10, 100, 1 million. how many fractures do we see in this piece of rock that you get a photo of it in your hiking experience, especially in Norway, the beautiful mountainous environment you have there. There are too many fractures to be handled. And now what is the state of what we do in the industry and academic places is characterize what are important fractures. I just did it by mouse. And then upscale the rest. Homogenize the behind matrix. That would give you permeability, the heterogeneous permeability that you would look like. And even then, your reservoir is at kilometer scale, and you're not going to be able to simulate this really with any advanced simulator here if you want to really capture the fractures that are all relevant for you in the kilometer scale reservoir. And here it comes that you need to cross the scale. You need to change the resolution even after this hierarchical approach, which means that you may not even go one level to the coarser, you may even need to go to multiple levels. And you may even need to go to dynamically multiple levels. So let's get some relevant questions before I go to the next 10 minutes of my remaining part of the talk. There are some relevant questions as a researcher. I need to be transparent in difficulties and in successes. We usually present success, but there are so many questions that still I don't have a clear answer. One is, are we looking at exact solution to the wrong problem in geosciences because of lack of data? So our problems, whatever we come up with, is wrong, is approximate. Exact mathematical solutions to them doesn't really have value if the problem is wrong. We are looking perhaps on acceptable solutions to possible realization. And that's one statement. The second is, what's the cutoff scale between homogenizing, making the background upscaled matrix, and the explicit fractures? Where do we put that cutoff? Where we say, this is the fracture we would like to have in our simulator explicitly presented, the others, please be upscaled. And is that a scale cutoff dynamically defined or statically defined? And the last is sensitivity analysis is, in my view, a lot more important than focusing on one realization. So having a convenient framework that allows you to change fracture geometries and the fluid physics and so would allow you to find out where do you stand in the entire system. And I rather go for something which is convenient for sensitivity analysis than for something that would be extremely fancy for one single given realization. And the last is how to cross a scale at the end. How can we represent this system in a lower resolution without losing all these features? Because we spent a lot of intelligence and cost to capture that plot. If we upscale again here, you're going to lose all the fractures. And then why did we do all these studies? So this is the last one that I'm going to spend a few minutes in the next part of my talk to finish the story. And then I would be pleased to have a discussion, lively discussion about this, and especially about the networks. And Alex already mentioned, but these are all the kind of exciting topics that we can speak about for hours. How do we cross the scale? I would like to set it right. First, we need to know what is it that we are crossing the scale. We have three characteristics within the unknown systems of our subsurface formation. We have local parameters that are saturation, temperature, enthalpy, failure, material fail locally. We have global quantities like pressure. Pressure is global, either elliptic or parabolic. It will be felt everywhere in the domain. Stress and deformation as well. And the two are coupled. The easiest way to describe an incompressible pressure equation is what's given in the top of this mathematical formulation. Divergence of fluxes equals source term. If you are communicating between omega-1 and omega-2, there is a psi term that is the flux exchange between matrix and fracture. It's a flux exchange between omega-1 and omega-2, if you write it for matrix. For fractures, the same. It communicates with omega-2, for it is matrix. Momentum balance for mechanical deformation under elastic deformation is also written as C, elasticity, Poisson ratio, gradient symmetric of displacement, which is a strain representative, and pore pressure based on BO theory. Transport, on the other hand, is local. Change over time of a quantity psi in omega-1 will have some divergence of fluxes and communication of the fluxes with omega-2 and some source terms. Now, with the first part of this whole thing, with the scalable part, the global people, pressure, displacement, there is a vast literature, and we have contributed on it extensively, on how to represent a plot of 44 by 44, which is shown on the right side of the plot, with only 4 by 4 points, without losing the structure there. And these are real plots. Local-based multi-scale approach started 97 by Tom Howe at Caltech in math, then Patrick, Song, and Ham did it, finite volume version of it, and I have been extensively busy with that development for many years and extended it for more physics and more different stories about it, is that if you have pressure or displacement, which is a scalable global component, you can locally solve multi-level basis functions. You locally solve basis. So if you look at the dots on the left plot, where it writes local domain, there are so many fractures and faults, I have put some black dots there. These are your sample points that will go to the course level. You will solve only for these points, not the rest. You make one of them 1, the rest 0. Another one, the rest 0. Another one, the rest 0. You find all these functions that are plotted as multi-level bases. Instead of upscaling, where you would find now the collective flux and would find an effective parameter, here you store this function, because that's how you would interpolate within that local region. You can do that for pressure, you can do that for mechanical deformation, but you cannot do that for transport. Transport is local, it has shocks, it has fronts. That cannot be done this way. What is being done in the fluid mechanics community and in reservoir simulation is that you do local grid refinement for transport. You go where the shock and front is, refine it, and use coarse grid wherever else. Now in geosciences, that is not convenient because we have heterogeneity, we have fractures. How can we go to coarse grid where I don't have fronts? Am I going to average the properties there? If I average the property, my global component, which is pressure, would be approximate, would be wrong, maybe. Then it would impact my local transport as well, because the two are coupled. So it is a kind of a way that you need to go to coarse grid, but your global component would impact not only the front, but everywhere else. So you need to stay accurate with your global components like pressure and displacement. For local components like saturation, heat transfer, failure, you can be local. And this is where we put the multi-scale basis look of the global treatment, combined it with dynamic grid refinement. And we did that modular operator way that I would like to skip here. But if you are given the black J delta X is F is your system, all the things that I'm describing here can be done with operators of R and P, restriction and prolongation. But it's more about implementation, not more about the concept. The concept is connected dynamic grid refinement, and when you decide to go to coarse grid, do not upscale, use the local basis functions. And that's all about it. And now you go back to this fractured rock, where you had already PEDFM, where the projection embedded was there. Your fractures here are all conductive, for example, and that's the pressure profile that you would observe with this embedded approach for heterogeneous domain. You have used 20,000 elements here, and now you cross the scale 3 levels up, and you only solve implicitly for 86 elements, and you interpolate with those functions, the basis, local basis, to get some plot that would fairly look close to this. Obviously, there are errors there that by eyes you can't detect, but that you should have a strategy to resolve it. We have a strategy, iterative strategy, that you can really resolve that thing. Now we put it connected with grid refinement, which means if I have this heat transfer with this heterogeneous system that I had before, now you have fine scale system for which the temperature distribution in this complex heterogeneous fractured reservoir would look like that. Now you have a toolbox that you can change the tuning parameter, the delta T, the error criterion. Do you want to go to high level or low level? At what change of temperature, delta T, you would like to refine your grid? So you would stay at the fine scale when you have fronts, and far from it, you go to coarse grid. And far from it, you go to coarse grid with local basis functions and not just averaged upscaled quantities. And we have benchmarked the two approaches with homogenization and upscaling with this multi-scale look with Sorin Pope, Mary Wheeler, and Musa and Manuela. Recently, just a few months ago, it was out in Advances in Water Resource Research. And how would the homogenization approach and upscaling would look different than this way of cross-investigating. So with that, you could go to more complex geometries again, as physics stays the same. You have fine scale fully resolved system, which doesn't have really error. So that's based on projection EDFM. Now you allow your system go to the coarse and fine wherever you want. So that would be how the simulation would look like. You are dynamically doing multi-scale basis functions. It is already created in the pre-processing step. You are using it for your transport processes and the pressure and the heat transfer. And remember, you're not going to effectively do any upscaling. You are going to resolve the fractures because they are important and they cannot be really upscaled. Even if, for example, you don't have front in this part of the domain or here in this view, it might be more visible. Even if you have decided to go to fine scale here you cannot homogenize that fracture because it may just give you a new permeability with your matrix. And then this might be already connected to some other channels and so. This is how you keep the heterogeneity and the fractures honored, even though you go to coarse grid with your system. And that's what we have just done recently this year. And the whole thing that I presented are all available online, but it's not just making them available online. We are willing to connect and adjust it the way that you would like to, or getting your insight, and we do the work here too as well. So it's either way, we have the interest to understand this process, especially the relevant geological features, networks, and the property. There was a question Marcel asked about how would you decide if this is impermeable or permeable. I asked the same question from my geologic colleagues. It's a relevant question, and we should be really, I don't know how, but I assume that if this is given to me, I can handle it. And there is, of course, I skipped the cyclicity, injection production, and porous scale relevant physics of it. This is the joint work we have recently done. And research assistant in our team, Leila Hashemi, is busy with the transport part, and a few others, Arthur, Nordin, and Kishon, are working on the mechanic hysteresis on this subject, and about connecting multi-resolution data to this. So that would be the next talks. But I hope that I kept the focus of this presentation on fractured reservoirs and introduce the topic of subsurface storage in general to this audience. So thanks very much. It was a pleasure for me to share what we know, and especially what we don't know, to you. And I would be pleased and delighted to have any feedback.
Thank you so much, Dr. Hajibeygi. It was so interesting. And is there any question from the participants?
Yes. This is Ali from Trondheim.
Go on, Ali.
Yeah.
We can hear you.
Yeah, thank you, Hadi, for your nice and interesting presentation. And I have a question from the part which has not been presented, and about the mechanics.
Oh, yes. Yes.
You mentioned that you have considered, or you plan to consider them, the mechanical part.
The mechanic part, the thing is, it's not unified and integrated in this whole package, but we have worked on it first with Nicola, Lawrence Livermore, and now with others who are here, Sarah and Fang Shang are working. We just recently did a multi-scale approach for extended finite element, where again, because we are somehow working on embedded approach, Ali. So yes. we are looking at enrichments of our mechanical interpolation. So there are two approaches that we are pursuing currently, and if you have interest, we could just on daily basis discuss with each other, is that you would like to know how many enrichments are necessary. Are you going towards XFEM, which would overkill all the additional nodes if you have tips and so, or you do finite volume based, only one enrichment per element for mechanics. We have tried both of them, and we have prototype codes for both of them. We need to understand before we put it into any relevant framework. At this moment, what we are doing is that the basis functions that I described that you would do locally, you locally solve extended finite elements, and no more extended finite elements from that level up. We have regular Galerkin locally computed basis functions that also mimic the extended finite element within them. So that's the under review paper that we have, and I would be pleased to send it to you. And that code is research code 2D, because at this moment we are trying to understand the concept before we do, the science of it should be first known to us. How much enrichment is necessary, and is it finite volume better or finite element, or which one is more convenient? That's exactly what we are working on.
Mm-hmm. And yeah, thank you. That was exactly my question, that you prefer finite volume for the mechanic or finite element. I personally, according to my experience, I have some experience in coupled THM models, and I think especially if you go for non-linear mechanical behavior like critical state models, I think finite element base extended finite element will work better in this coupled process with non-linear mechanics, and I will be happy to discuss more on this with you, and I will contact you.
We have a paper on arXiv, and so what we have done for the cyclicity, we have done all finite elements. I have a student who does a finite volume. I have a paper also a year ago with Irina on finite volume mechanics with JCP. Finite volume is interesting, especially when you go to momentum and the crack propagation, then you are solving a transport problem of momentum, and maybe conservation maybe helps, but this is the scientific approach that we are still pursuing. And what I can say is that even the contact mechanics, when we did it with finite element, it was well behaved, and so we see benefits of the both, but also are curious to see if finite volume would also be able to be working on that side. But absolutely, I mean, this is exactly what we are also having a lot of interest, especially for the Groningen gas field that you have heard maybe in the north of Netherlands. We have now 15 PhD students at Delft who are working on induced seismicity, different aspects of it. So it would be absolutely a relevant topic if you wanted to discuss and connect with us.
Yes, thanks. Absolutely. Thanks. I will contact you soon.
Absolutely.
I have a couple of questions.
Of course, please.
The first one, I just didn't catch what you use relative permeability for in this story.
Oh, for the transport, for the properties of the dust.
But I mean, this is heat transport.
Oh,
so it's dispersion,
heat is
right?
coupled. No, heat is coupled with flow. So we inject fluid, cold water. We inject cold water into a hot reservoir. So you have a flow, which is the Darcy law with fluxes and everything. And then with the heat transport, you have change over time of your internal energy for fluid and for rock, plus the enthalpy convection, plus the conduction, and then the source terms. So it's a fully coupled flow and heat transfer.
Yeah, I would have seen it differently. This is a dispersion problem, right? With okay, the fluid is changing properties when it changes temperature and so forth. But
you are injecting a cold water into a warm system. So your front of water is actually moving.
Yeah, but that's a dispersion front. It's heat front.
No, we have two fronts: mass, I mean the cold water front, and the heat front. The two.
But you have zero capillary effects here. So why do you use relative permeabilities?
For that, steam and water, you mean? Where the interfaces. Actually, this is one thing that you would assume, that since it's water, you would say it's only different phases of the same matter, like brine and vapor water. Still, the water is brine with minerals. What I am hearing is that it is not trivial to assume that there is no surface forces there. Again, what we are doing is that you would say, it's more about linear relative permeability curve, so no interfacial tension between them. Apparently, what I'm again discussing, I could also connect you with them who are doing more field-based geothermal. It's not trivial to assume that it's linear. We are using, I mean, you can use linear functions just to assume, but apparently it's more complex. And this would be a subject that if you are interested, we could also have a kind of discussion with Thomas Drisner at ETH and others at Auckland as well. It looked to me like this before, but I didn't know it's really valid. So if you think it's valid, still we are two of us. But.
And then how do you deal with fracture permeability? How do you model that? How do you assign numbers?
population of the properties at this moment, what we do is we just decide based on the stress field, the work that Mark Zoback did some years ago. We decide the stress field in the reservoir based on the threshold value. We say this is open, this is closed. Those which are closed, we just randomly distribute impermeable or permeable. Those which are open, we just randomly again give some apertures to them.
You turn it into a percolation type problem.
Precise.
Yeah. Okay.
But I had a master student just finishing done who did this geologically relevant fracture property population. I think this for me is I'm just starting to learn the geology of this whole
yeah
thing.
Because you know there is non-zero literature in the physics literature on fracture permeability where they have joints or faults, for example.
Yeah. So I am those who would do this search and find this. I can't reach those, so I have plenty of these questions that.
Yeah. I worked quite a lot on that myself.
Great.
As for fracture networks, we developed. We try to answer the following question. Okay, so you're given a fracture network. How do you put numbers on it? I mean, how do you characterize the topology in a quantitative way?
Yeah.
Because of course that is the key to generate artificial networks, because then you can actually use the numbers to compare the model to reality.
Absolutely.
And the way we did it was simply to map it onto a network of links. So we the fractures were nodes. We mapped onto nodes, and then whenever two fractures were crossing each other, then we put a link between them, and then we got a network. And then suddenly we have access to these tens of thousands of papers that's been written now on network theory.
I see.
So we do know hundreds of ways to characterize this.
Yes,
and that worked out very well.
I look up your work on this subject with a lot of interest. And from our side, we did it very much, computational geoscience part, and less of the geological relevance of how to populate. We say if it is being populated, it's going to look like the geological outcrop that, let's say, our geological colleagues have done. Then we should allow for all these embedded approach, and we should allow for crossing the scale. And now we are exactly at the time that to say, how are we going to populate these properties more intelligent? And the work you mentioned would be extremely helpful for us. Absolutely.
Yeah. Okay, thank you.
Very good. Thank you, actually, Alex, for this very nice contribution.
Any other question? Okay, thank you so much. And yes, have a nice day.
Yeah, you too all. Thank you very much. All the best. Bye-bye.
Bye.